Okay. Should I begin?
Yes.
Yeah. It's working. Yeah. There we go. Yes. Hello.
Hello.
Everyone. It's pretty good turnout. I like that. I'm Thomas, better known as Tjoppen in these parts. And there we go. And this talk is titled Space Hacking: How to Design Hardware on a Shoestring Budget That Hopefully Survives the Lunar Night. And so I'm going to talk a little bit about us people who are behind this. So it's not just me who are involved in this thing. So we're a bunch of Swedes who formed a group that we've called Space Science Sweden, just as a name. And we're mostly people in Umeå, and it's mostly hackerspace people. So Umeå hackerspace is a thing. You can go check us out. And elsewise, it's model rocket enthusiasts and space nerds, and a couple of radio enthusiasts, and a few PhD students. We have one in computer science and one in physics that's working on this thing. And we have a website, scube.se, with a simple WordPress blog. So we try to keep that updated about once a week. This talk is about the moon, and you may have seen it. It's that thing in the sky. It looks like that. And let's get the pointer out of the way. Oh, okay, can't do it. So I'm going to start with some moon facts. So it's a little bit away, just over 1 light second, which means that the signal delay, if you're running something up there, it's about 2.5 seconds. Until you get a response. And of course it's smaller than the Earth, it's lower gravity, so that has some implications. And it's tidally locked to the Earth, which means that its rotational period is the same as its orbital period, so it's always facing the same way, which you may have noticed. You never see the far side of the moon, you always see the near side.
From here?
Yeah, from the Earth. Unless you're part of the Apollo crew, no human has seen the far side of the moon. Incidentally, there's no dark side of the moon, unless you count the night, then, because since it goes around you have days and nights, which actually ties into the next thing. The days and nights are 2 weeks long, roughly each. And the days are really warm, so 130 Celsius, roughly, depending on how high or near the equator you are. And the nights get even colder. So especially this coldness is a bit of a problem. For instance, the Chinese at the moment have large problems with this. And it's dusty. And the dust is like electrically charged, which tends to stick to stuff, and it's really, really fine. It gets in everywhere, and it's a bother. And it's a vacuum, or it has an atmosphere, but it's so tenuous that for practical purposes, it's a vacuum. And because it's a vacuum, there is no atmosphere to protect against radiation. There's no magnetosphere to protect from the solar wind, so you get quite a bit of radiation. So that's a bit of an issue as well. I'm getting to why am I having this talk, and it's due to the Lunar X Prize. How many have heard about this? It's about half or so. So it's a competition, let's say. There's a website for it. And it's basically land a robot on the moon, then move 500 meters in some way across the surface, and transmit HD video back to Earth.
Does it have to be a robot?
Well, technically no, I guess. Are you volunteering?
How about a dog or something?
Maybe we can train it to have a dog spacesuit. That would be interesting. Maybe a small rat or something. It could work. So it's the first one to do it wins $30 million, or maybe everyone does. I'm not sure if it's only the first one or if everyone that actually succeeds wins it. But there's a grand prize, and it's to motivate people. It's nowhere near what it actually costs, as far as I know. And yeah, there are several teams. I think it's around 18 at the moment, or 13, something like that. We're in the race still. And yeah, they have pretty different approaches, as we'll see. So these are a few of them, and their craft. So the top row are all rovers, pretty typical. You have the or Barcelona team, who has and you have the part-time scientists, which is mostly Germans, but it's I'd rather say it's a European team maybe. And you have the Japanese team Hakuto, who has 2 rovers, a big one and a small one that they're going to lower into a lunar cave. So they're going spelunking. And they have a little bit more untypical. The Lunar Lion, Penn State University's team, they have a lander. They're going to land it, and then they're going to lift off again, like jump 500 meters. So that's risky, but fewer parts, trade-off. And you have the Space IL, I think it was, an Israeli team, who are doing a similar idea, I think. This one is very, very small, as far as I understand. And you have, as well, the last one here is a Moon Express. And I don't really know what this is. It's like a station, or like a base. But yeah. So there's even wilder designs. I just picked a couple. So this talk is due to part-time scientists, which is these guys. And yeah, they have an IRC channel. So if anyone has a phone with IRC, you can hop into the channel and ask them questions. I hope they're back. I'm gonna check. Yeah, okay, yeah, he's back. And and also during the question phase later, that'll be useful. And they have a website, of course, ptscientist.com. And they've cleared several milestones. They seem to be in a good position, so that's good. And yeah, they're doing a rover, or actually 2 of them, they're called Asimov. And they're landing at the Apollo 17 site in the Taurus-Littrow Valley. Yeah. So how many watched the 31C3 talks? A couple. Did anyone see this talk? No one, okay. Good thing I have it explained what it's about. So these guys went to 31C3, and they basically said, hey, we have space left over. So like 20 kilograms worth of stuff can be sent up. So in what they call drop containers. So there's 4 of them of 5 kilograms each. And basically, they want ideas from the public, because they're like busy enough, as I understand it, to begin with. So they're looking for motivated people who want to build stuff for that. And they have a deadline for April 30th, which is kind of close. And yeah, we've been working like crazy, me and the other guys. And yeah, that's where we and all of you guys come in, and anyone watching. Let's see, where am I? Yeah, I'm there somewhere. Yeah, so to try and explain how it works, this is the rover without the solar panel. So the solar panel goes here, and it tilts on this axis. And to stabilize it during launch, there are like some structural elements here that goes along that they then want to get rid of, so they can tilt the solar panel for better coverage. And these things are shaped like Toblerone boxes, like oversized prisms, 480 centimeters long, 40 centimeters sides. Provide solar power basically they open up 2 of the sides, and on them there are panels. So you get, I don't know how much power, but it's in the 10s or 30s watts or something if you calculate it using regular solar cells. And they have a downlink of from a few kilobits up to like a megabit or something, depending on how much it's things, but only during the day, which is relevant for us. Yeah, so it's 4 containers, 5 kilograms each, as I understand it. I don't know if this is the entire thing or what you can have inside it, but it's yeah, it makes some difference. You have to deal with all the problems of getting there, surviving like 3 days in transit or whatever it is. I think it's something like 3 days, and of course on the surface. And you have to coordinate with them, of course. So yeah, I have a bit of an open question here. What would you send? And I think if anyone, do people have like ideas? If you have an idea, you can just shout it. Or maybe they're a bit shy. I'll let you think about it because we'll have a question thing later, and you can like ponder it. I'm gonna check where I am. Yeah, there somewhere. We asked the same question, and we've been like brainstorming and talking to these guys and going back and forth. So we had some awesome ideas, which turned out to not be so practical. So one is doing ISRU stuff, which is basically taking what's on the surface and doing stuff with it. So you take the regolith and you try and distill it in various ways and build things out of it. And one is, of course, a 3D printer, because everyone likes 3D printers, which basically works well around either of these concepts, which is you can distill sulfur out of the regolith, which you can then use as a binder in a concrete. So you mix those two, and then you heat it, and then you can extrude it through a nozzle and build things with it, just like a regular extrusion 3D printer. And another way is to use sintering, which means you just have a laser that goes and melts stuff. And I think the laser thing is easier to build because you just have to have two mirrors and do an XY thing, whereas this needs all kinds of mechanical stuff. Yeah, and another idea I had was to do some electrolysis somehow. I'm not sure quite how, but basically you scoop in some regolith and then you heat it up with like a laser or something, and you pass current through it, and you can extract elements. And you get titanium, aluminium, silicon, oxygen, and especially like aluminium and oxygen makes for a rocket fuel. So that's very, very relevant for future activities. And of course, we had the idea for a robot arm, because if you have a 3D printer or something like that, you need to be able to scoop up regolith and put it into like a hopper or a sieve or something, and you need to do all this stuff. But it's too complicated. It probably won't survive the journey, and there's like too many axes of rotation. It'd be cool if someone could figure out how to build it, but we don't have the time, unfortunately. So, and yeah, everyone suggests these. Radio isotope thermoelectric generators powered by plutonium or strontium. And my usual answer is sure, if you build it and get all the permits. But yeah, we're not going to do that. It'll be fun though, and dangerous. I like dangerous things. And yeah, every now and then we get into the rover territory, which we realize is also too complicated. So we're not going to do anything like that. It's too complicated as well. Yeah, we have some ideas that we considered for a while, but eventually ditched. One is to use a flywheel to store energy, because it doesn't matter about the temperature. So unlike chemical batteries, it doesn't matter if it's hot or cold. But it's a moving part that can break. And it also requires passive magnetic bearings, which we have found one supplier in the world for. And yeah, but it could work. It could potentially work, but yeah. And the other one is a hydrogen fuel cell, which we realized if you have a high enough pressure, it's actually useful, and you can make a self-contained unit that weighs maybe a kilogram or 2 or something like that. But the problem is the valves and sensor weigh too much, and you need, if you want to maximize efficiency, you need spherical vessels. I managed to figure out anyway. And maybe you don't actually need it, but these are expensive, and it's dangerous, high pressure, and it's not that high energy densities compared to good batteries. Not enough to warrant this complicated thing. So we have some doable ideas. And the primary one we're working on at the moment is to provide power during the night, and primarily through keeping regular batteries, like keeping them warm, or relatively warm, maybe just minus 25 Celsius or something, or 0 Celsius, somewhere there, such that they don't freeze to bits. And of course, thermometers, these are like linked. So we want thermometers to monitor how the health of everything. So these should be pretty simple, or simple-ish in this context. Of course, cameras, everyone likes those. Yeah, both for looking around and getting some 3D view of stuff. That would be really useful. We had some experiment ideas around stereoscopic tracking of particles and things, but we'll see if we have time for that. And of course, magnetometer. The moon's magnetic field is kind of unusual in that it's very low and it's localized. So you don't have like a global field, you have local pockets which are rather weak, so that could be interesting. And yeah, one thing the PTS mentioned as well is figure out something that they've tried to do in the past but failed, and try it with like new technology or something like that. And one is gravimeter stuff, like measuring gravity, which they did but had some problems apparently. And there are some other things you can do. So the stuff like that would be interesting. Yeah, how hard can it be? It's not rocket science. Oh. So there somewhere, good. But how hard is it really? So when you start to dig into this, like what are the actual problems and what you need to figure out? So yeah, it's basically like building an amateur satellite. Does anyone remember the TRSI sat from 1 or 2 years ago? Yeah, last year, okay. Yeah, that failed recently, apparently, due to power or something. So that tells you some things. But there are similar problems to begin with, because you're still launching with an old ICBM, and it has quite high continuous shock or continuous acceleration, peaks at around 8 Gs, and every time it stages, you get 1000 G impulses. I'm not sure if this actually translates into the payload, because I suspect they have some suspension and stuff. That's what I would do. But still, so it's a bumpy ride up, and yeah, as well, temperatures problem. Especially, it's 2 weeks of each, so you need to think about. Unless you only plan to work during the day, and it gets a little simpler. Yeah, radiation problem. All logic, like unless you think about it and take steps to prevent it, you can get it stuff like you can get a cosmic ray, like a charged particle, proton or something, goes in and flips some state. And the worst thing is like if it flips a pin, so it'll drive up and start something. You don't want that, like accidentally turning on the heater or something, and then draining the battery. So you need to think of that. Yeah, vacuum, of course, some various issues. And of course, dust, again. Any movable parts will be problematic, especially if you can't like have bearings, or you can, I think. I haven't looked that up so much, but I know the Russians had problems with this when they made their rovers in the 70s, so yeah, that's a bit of an issue. So yeah, keep it simple, stupid, and test as much as you can. And again, no robot arms or 3D printers or plutonium. That just gives you trouble. So we have some reading, because of course there's a lot of stuff to get into to figure out how what it's like. And the most important thing is the lunar source book, and that's what PTS suggested. And if you just search the web for lunar source book and you get it, it's like 300 pages. The first 2 or 3 chapters are the most relevant. That's like 50 pages or so. It tells you a lot of the stuff that I have in this talk is in this book. So yeah, stuff like temperature, how like compressible the soil is, how the grain sizes are, and everything you'd like to know about walking around out there. Another thing I found kind of useful was the Planetary Landers and Entry Probes book, which is also on PDF somewhere on the web. And this has this is like a guide for making a probe. And they have all this like thermal, how to design the thermal stuff and figure out the like your link budget for your radio and all that kind of stuff. So that's very healthy to read, so you don't make a lot of mistakes that have already been made. Yeah, anything on past missions. The Lunokhod missions are rather interesting. That's the Soviet rover missions, rather successful. The lunar roving vehicle they had during Apollo 15, 16, and 17. The Chinese rover is unfortunately they're kind of tight-lipped still, so we'll have to wait a few years probably, hopefully. And then you have the probes they sent before the Apollo missions, like the Ranger, Surveyor, and Luna probes. And especially the Luna probes had a lot of failures, so that's interesting to read about all the engineering mistakes, let's say. And also, you have the user manual for the rockets itself that they're going to use to shoot up the thing. And as I think it was Michael in the team that said that everyone should have the manual for an A-bomb at home. So, it's kind of fun. Talk to people. So it turns out, like, when you start asking around, there's a lot of people who know stuff that is very useful. And with niche knowledge. So we went, for instance, and visited the local radio hams, and they had a lot of good tips about radio stuff, because we realized we need to have some radio link during the night just in case. And they had a lot of good suggestions, and we got some leads there. And we have another guy in town who's like a hobby vacuum person. He builds all kinds of crazy things, builds Tesla coils and jet engines and other stuff. So he got really excited when we told him about this project. And that's one of as a vacuum chamber we're hoping to use for our tests. And it's kind of fairly big. And that's a small one. We tested a cell in just to see what will happen in vacuum. And it turns out you need to actually protect the cells, at least ones we have. And so we have two basic goals. And one is to survive and operate during the lunar night. It's 354 hours, or just over 2 weeks. And the second is, of course, to have some useful energy to run stuff, like sensors and radios and what have you. So this presents a lot of challenges and problems for engineering. And of course, electronics is important because that's what we use. We don't do mechanical stuff or clockwork, not anymore, at least, not much. And of course, a bit of mechanical engineering is involved, and thermal design, again radiation, and again vacuum, and of course, in our case, radio, since we want like a backup link. And so first. Electronics, redundancy. At the moment we're trying to design so it has dual everything. So like dual battery packs, dual processors, dual like transceivers, and all that stuff. And we're trying to keep the low-level stuff as analog as we can, especially the thing that regulates the temperatures in the batteries is at the moment just a really, really simple thermostat circuit, and all it does is it pulls low when it gets cold, and you can drive a MOSFET with that and keep the temperature in a reasonable. Even if everything fails, it'll start in the next day or something. And again, we have the analog as a base system, but we want to be able to override it if we want to, for instance, run it even lower temperatures or higher temperatures or various stuff. And you need to be careful, because if you have a crash, you don't want it to get stuck with the heaters on and drain the batteries and then they explode or something fun. And as well, similarly, short circuits, that's a common problem. One simple solution: use constant current diodes, or current regulating diodes as they're also called, which is basically a diode that won't let current above a certain limit through. So it's like the opposite of a Zener diode. So these are kind of useful as a sort of automatic, not an automatic fuse, but something like that. And then the ability to turn off different parts. So if something fails, then just shut it off and not use it. And then also a typical problem is, if you repaired electronics, you may have noticed that it's quite common that 2 or more pins become shorted. And you should, at least we're trying to do that, like trying to design it so that even if any 2 pins on each package are shorted, it won't like fail, except maybe some central part, but you'll have to take some risk. And this is a problem they're having with the Curiosity rover on Mars at the moment. Or similarly, it's not fatal, but they're having to work around it, I think. Their robot arm is having problems, it turns out that's a difficult problem. The mechanics, and few moving parts, the better for us at least. We don't have any at the moment, and bearings are problematic. The Russians use something with a fluorine-based lubricant and all kinds of fancy stuff that I don't want to work with, and no one wants to work with. And if you have movements, try to keep them as simple as possible, which, again, no robot arms, is, unfortunately. And again, we're planning, at least for our stuff, to just encase it in some resin or potting compound to try and contain it, to keep vibrations from destroying it. And then our major concern are thermal stuff, and it's you have conduction and radiation. Those are the primary ways in which heat can move, since you don't have any air, so there's no convection to worry about, at least. So radiation follows Stefan Boltzmann's law, which is basically just an emittance value, which depends on the material. So if you have a reflective material, it'll emit less thermal radiation compared to something that's black. And one product we found had 3.5% as a value for that. So that's good. And the sigma is just a constant. A is, of course, the area of the thing you're considering. And this is, of course, temperature in Kelvin raised to the power of 4. So this, especially this term, is problematic. So we're trying to keep temperature as low as possible to not have to heat it so much, but to still have to keep it at some level that it doesn't destroy itself. So we came up with this number for now, for our current dimensions. And it turns out that, in this case, 285 milliwatts is barely within the limits of what you can do with just commercial batteries. And then you can get fancier silver zinc batteries and stuff. But for now, we're happy with this. And 0 Celsius is reasonable. And of course, conduction as well. So anything that touches will conduct heat, and it's proportional to the conductivity and the area, and inversely proportional to the length. So we're looking to have perhaps some ceramic pegs or something that it stands on to minimize the contact. And luckily, regolith is a poor conductor of heat, so it saves us a little bit. But we need to calculate or simulate that a little bit more to know. And otherwise just use components that handle larger temperature swings and all that. So we have our first prototype. It's very basic. It's just for testing the concept, and it's just a lithium-ion cell with a heating pad that we made out of some resistance wire and masking tape, and then we have a little controller board and a simple 433 megahertz transmitter, so we can monitor it. And we stuck this in a thermos, put it in the freezer. We came up with a number of 800 milliwatts, but that's it's not a vacuum and it's not perfect. So we're expecting this number to go down quite significantly when we can actually test it in the real vacuum chamber. So we'll see how that goes, and that's what we're doing at the moment, working on a bigger prototype with 8 batteries, and they have heating pads and temperature sensors and the aforementioned thermostat thing, and of course it's held together by hot glue, and that's always good. That's very scientific. So and there's 3 other things, and it's radiation. You can try to shield in a way, try and use lead foil or tantalum foil. It can get heavy. We're not quite sure how much that will have to weigh. You can try and work around, if it hangs or locks up, you can try to have it maybe you can reset it or something. But importantly, if it gets stuck, it shouldn't drain the batteries or something. And luckily you can get radiation hardened silicon, and it doesn't seem to be in stock everywhere, but it's not that expensive, the ones we've found, except certain manufacturers that make super duper reliable ones you can get. We found, I think Atmel sold some for 10 or 20 euros a piece for processors, and I was what? That's way cheap. how does that work? So we must have made a mistake or something. I don't know. We'll have to try and order some and see what happens. So that's further down the pipeline. And if you have high vacuum, or in this case ultra high vacuum, which is an entire field, as we've learned, and there is an atmosphere, but it's in the picotorr range, which is like, I forget what the torr is, but it's there is some atmosphere, but it's not for our purposes. There isn't any. But yeah, no liquids, they will boil immediately. And yeah, volatile substances, something like if you have like a petrochemical thing or like a carbon containing thing, they can like boil. And if you have like a pocket or something, it can collect there. And you'll get a little atmosphere there. And if you have like a high voltage part, that can cause discharge. And that's what happens to one of the Soviet Venus probes, the Zond-1, which the radio in the satellite failed because they had a leak. So they had a pressurized compartment in it, and the pressure got into like the sweet spot for generating these sparks. Luckily, they had the transmitter on the lander. I think that's the lander. I'm not quite sure. So they were able to run it anyway. So that's good engineering. And yeah, we need a radio, and we'd rather not have to need a radio, but yeah, because the lander will not be running during the night. And we're not sure if it'll survive. Otherwise, we could just save to a memory card and then transmit it during the day, but we'd like to cover all bases. So we're trying to use the onboard radio that's going to be on there, so the one that goes from the lander to each container. And the reason is, I'll get to that, is first of all, the problem is that it's quite long distance, which means that you have the inverse square law for like path loss, so that gets rather high. I forget the number now, but you can make a comparison. So in the amateur radio world, they have people who bounce signals on the moon. It's called Earth-Moon-Earth communication. In this case, we only have half the distance since we have the transmitter on the moon. So it's actually easier. It should be easier. So we should require a lot less power than they do. And that's good because we don't want to waste power. And we figured out that we probably want an omnidirectional antenna, because if we have a directional one, we can accidentally like be dropped incorrectly and not be pointed the right way, and then it'll be worse. So at the moment we're thinking that if we're going to use something like that, we just compensate with a larger receiver and more power on the ground. And but still, it's going to be pretty slow. At the moment, it's like 31 baud, perhaps, maybe a kilobaud if we're lucky. And analog modes will probably not work, we've been told. So it's gonna be some digital mode, maybe some error correction in that case. So we can do some experiments on the ground and see if it's even possible. So hopefully it is, but that's in the future. And pretty much, it's getting close to the end here. It's good. So you need to test stuff, and you can simulate, of course, and that's what we're going to do. We're going to try and draw up some CAD stuff and try and simulate it, and that's cheap and easy, relatively. Otherwise, you can try and find like a testing lab. I think the nearest one from us is in Luleå, and that's 300 or 350 kilometers north. That's a bit inconvenient. You can do as us, build your own gear. So you need to test for the daytime. So you need a vacuum chamber with like heat lamps. And if you're going to run on the night, you of course need a cryogenic version of a vacuum chamber, and this is considerably trickier. And some kind of shaker thingy, like a shaker box, or we're thinking like just having a PA system. You scrap a PA system and you strap the thing on the speaker, just crank up the volume, and maybe, we'll see. So the thermal vacuum we expect will be easier, because we whipped up a really ugly thing with 800 watts of halogen tubes. That gets warm enough that the MDF, which we're not going to use, it starts smoldering. So we're pretty sure we can reach temperatures that are correct if we just position it rightly and adjust it. So that's not a huge issue. The real problem is the low temperatures. So we've been talking about that, and we figure one thing is this thing, we can have cooling tubes, what's it called, copper pipes on it, and then we could like pipe acetone that we pump through dry ice. And then you can get the temperature down to like 80 Kelvin, no, not 80 Kelvin, it's minus 80 Celsius, something like that. And then you have to keep adding dry ice though, that's a bit inconvenient. And another way is to have a liquid nitrogen bath. So you pour a big old container of liquid nitrogen, you lower your thing into it, and then you top it off as needed. And that's also kind of inconvenient. It'd be nice to not have to do that. So we got recently contact with a guy in the dairy industry, and they have a freezer that apparently goes to minus 80. So that we might get to borrow. The problem is that our vacuum chamber might be too big. So we're hoping that's not the case. I'm waiting for measurements, but in that case, we put that inside, and then maybe put like a Peltier cooling rig inside that. So we pump it down even lower if it's possible. I'm not sure yet, maybe not. It'll be difficult either case. Yes, so what else kind of problems can there be? And of course, there's lots of things that can go wrong, and I know I don't know everything. So yeah, try to read as much as possible to sort of figure out what's gone wrong before and try to avoid it as much as you can, as cheaply as you can, unless you have a lot of money, in which case just spend away. Yeah, you need to pick something that you can actually do by the end of the year, at most a few months into 2016, because they're, as I understand it, they're shipping the stuff over to the launch provider sometime during next spring, so in about a year from now. And you can't like touch the stuff after that. So yeah, the lighter the better, and the less power you use the better. And if you want to use during the nighttime, that we're hoping we can get the system together, you can get maybe 1 or 10 kilojoules, and maybe 1 baud or up to a kilobaud per module if you have to like share the data link. So this number is not so happy, but maybe you can make do. I don't know. We'll have to think about that. Yeah. Oh, yeah. We're actually looking for people. It's always a bit of a problem because we're never enough people, or at least in our case. So we, for instance, need people who know about radiation stuff, how to like shield against it, and maybe how to build test gear or have access to test gear. PCB design is a little simpler. Something like automotive, I don't know. People who know how to write stuff for embedded systems and real-time operating systems. Packet radio guys. Maybe if someone has ideas for some novel science thing, you might as well also contact PTS about that. And maybe if someone's interested in PR, that could be useful. We're not overly concerned with PR, but you might need some, because we might need partners if we get on board. We'll see how it goes. We don't know at this point, but we might have to buy stuff that is expensive, and we need some. Can't. Yeah. Yeah. Questions? Let's do that.
Oh wow! Scary microphone. Is it necessary to both transmit and move at the same time? Is power shared between both the radio and any motors going to be an issue?
Well, this thing is standalone, so we get dropped off somewhere in that case. So you're on your own, which means, yeah, motors use a lot of power. So, and we're not going for any mechanical parts in the container, at least not our stuff.
So
but it all plays into the energy budget.
So is your plan then the rover is going to transmit locally to a centralized little base, and that's going to do the broadcasting back to Earth?
Yeah, the way I understand is they have the lander, and there they have the proper antenna system, like the S-band system and the X-band, and then you have a little dinky little transmitter on each little on the rovers and on the drop containers that transmits to that, and then it relays it back. And I guess they can put a lot of power into that transmitter. Like it's kind of big. I don't know how big it is, but I'm expecting they can put several watts or tens of watts or hundreds of watts, whereas we might want to run on 1 milliwatt or something like that. And we're not quite sure yet if we can pick that up. So we are trying to figure out a way to test that. And yeah, that's tricky.
Yeah. So is line of sight going to be an issue? Because I mean, the moon can be quite a rough surface.
Well, they're picking landing sites since they're landing at Apollo 17, and the Apollo sites were chosen to be as flat as possible because they couldn't handle more than 15 degrees or so of difference, and they couldn't be too large boulders and stuff like that. It's pretty good, as I understand it. But yeah, that is an issue. Like if it lands on a slope or something and they tumble down, it's game over.
Yeah, thinking of particular probes that bounced or landed funny on a comet, maybe.
In our case, exactly. Philae. Yeah, we'll see how it goes for Philae. Hoping he survives. But in our case, we're lucky because we get dropped from the rovers. So the lander goes and lands, and then it drops the 2 rovers, and then those go off somewhere, and they drop 2 containers each. So that can be controlled. So you just drive somewhere. It's like, this is flat and nice, and it's in a good angle to the Earth, like for the radio stuff, and perhaps to the sun for thermal reasons, is what we're imagining are the 2 most important aspects. So yeah, it's not you're not randomly throwing them on the surface, luckily. As long as like the lander makes it, it's relatively home free, kind of, maybe. We'll see. But yeah, that's a good question.
I think I read somewhere that the Apollo landing sites aren't they like sites of cultural significance that you can't touch? Is there a danger that you might crash land into the American flag, or?
That is a risk, but I don't think it's kind of a small spot compared to the size of the moon. So, or the size of each lunar marea, like all the lunar lakes that they've landed in are kind of large. So it could happen, but they've, as I understand it, they've developed a series of like rules, like don't go too close, like don't drive over footsteps and stuff like that. But one of the goals, or one of the sort of sub prizes, is to photograph one of the landing sites. So I guess that's what they're aiming for, because get some extra money and it's cool. And apparently they were in the committee that worked out those rules. So I think that stuff is not so much to think about, unless no one can stop you. Like, what are they going to do? But on the other hand, you won't ever get into the United States if you go and ruin their culture heritage. So you'll just have to pick whichever is more important. See, there's back on I see at least. Well, there's no more slides, so it's no problem. Any more questions? Maybe some. No. One more.
Yeah. So you just I'm sorry. This is totally new to me. So perhaps you're going over things that people already know. So the lander comes down, sends some rovers out. They can drop things along the way, continue on your way. I'm not sure if I really understand.
I should perhaps have drawn a diagram. That would have been helpful.
Maybe next year.
Yeah, maybe next year. Maybe if we actually get space on board, and then we can talk next revision. Like, here's what we're going to do now. We're going to build a 10-meter diameter dish to receive the thing, and we're hoping that it doesn't break or something. I don't know.
So how much are you planning ahead of time as to the routes, and you know the topography of exactly where you're going to land, versus you don't not exactly sure where you're going to land, and then you have to play it from there and say, okay, we've landed, we've got this orientation, what's the topography, what's the best path to take, and then encountering boulders or cracks or whatever. You know, it sounds like you'll have to do a lot of stuff on the fly, which means risk.
Yeah, first of all, that's not my concern, luckily.
Oh, pass the buck, nice.
Yeah, I don't have to care about that. That's the nice thing. I just put me down there. That'd be good. But that is actually an issue, because if you look at, say, Apollo 11, they had a landing site they were shooting for, but then when they looked out the window, they were like, this is too rocky. Yeah, so they had to like glide a little bit longer, and they almost ran out of fuel looking for a better place to land. And I guess all the robotic landers have ground penetrating, or like ground radar, so they can look at the ground and see like, this is even enough, let's land there. And yeah, that's up to, because of the signal delay, you can't like do it live. Yeah. Or maybe you can, but you're not going to do it live. And so you're just going to have to rely on the program, figuring out where a good spot is. And probably, I don't know, you can imagine that being tricky, like as the fuel runs lower and lower, you'll have to be a little bit less picky.
Yeah, and that's just the lander, let alone the probes or the rovers moving around, picking out paths, or whether you're controlling it by hand.
Yeah, I think they'll be controlled by hand. Then they move rather slowly, like 1 meter per second or so. So it's a nice steady pace. And from the Lunokhod mission, I mean, it's not that hard to drive apparently. Well, it requires some training, but you can do it. And as long as you have good eyesight, because that's one of the problems they had. Like they had the cameras too low to the ground, so they couldn't see where they were going. But this one has the cameras high up, so it's a little easier to get a good view, so that should be less of an issue. Yeah. But yeah, it's definitely tricky.
So you said you're going to use 2 processors, but now I'm asking, how do you get out if one is 40, so you can't really do a majority vote? On the other hand, you have to judge it against 3 processors, which need a third more energy, of course. So have you been thinking about that already, or is that just, one backup and it should work?
Well, it depends on what you're doing. Like if you use, for instance, a CAN bus, so you're talking to the sensors, and they're posting messages to your CAN inbox. And each processor, you have dual buses, for instance, and then you have dual ports into the buses. The thing is, the problem it's both a power problem. If you have dual processors, you're having dual energy use, and as well, if you perhaps only have one radio, then that becomes a problem. If you have 2 entirely separate systems, then it's not a problem, I think. But I don't think we'll do that. We'll see how it goes. We'll have to figure that out. But at the moment, we're thinking something like, maybe you can shut off one processor if it's behaving incorrectly or something. You can try and make one the master processor, but then if that fails, it can quickly become complicated. So, that's a good question. That'll have to be solved. We've been discussing it a little bit, but we haven't come up with a perfect solution yet. But you're free to take the task. Or something.
I think part of the question, the other half of the question is that if you only have 2 processors, how do you determine which one is faulty?
That's a good question.
I think that's the gist of the question.
I think what we can do is something like have one that's always running, and you can use a watchdog timer or something. You have it resetting every now and then. And you have one as just a backup, perhaps, and the other one as a primary. And if the primary doesn't start within a minute or so, the secondary starts. So that might be a thing. So it's only either one of them running. That might be a working solution that also doesn't use any more power.
That's something you could simulate, though, here.
Yeah, you could just try and disconnect the cable, see what happens. and try and short two connections, see what happens.
Well, we can play the game with 3 processors again. You can say you have 2 processors running, and if you get any conflict, you can fire up the 3rd one and say, what do you think?
Yeah.
So
yeah, okay, yeah, that's true. But I think something like you start them in sequence maybe, and if one of them fails to boot, then the other one takes over. I think maybe something like that would work. That's something I think would have to be fiddled around with to figure out a good solution.
Yeah, it's just the problem if you have something less crucial which breaks. Like booting up is easy to determine, but let's say one processor says, let's turn on the battery heater. So maybe that one doesn't work, and you can't really detect it because you don't have any corrective.
Yeah, what you can do is you can have multiple one of the ideas I have is to underspec the heaters, but to have multiple of them so that if one gets stuck on, it's still not enough power to keep it warm enough, so the other guys will have to still, like it won't get too hot anyway. And it's like they maybe have 4 of them, and they're controlled in pairs by each processor or something. You can like sort of play musical chairs with this stuff quite a bit. So I don't think we've figured out exactly the best way to do all that stuff yet, but we've discussed it at least, and there are multiple ways of doing it. And I think maybe trying to just run one and then have a really stupid, like a watchdog timer that tries to start the first one, and if it fails, it just after some fixed delay, it starts the other, and maybe that'll work. It'll be interesting to experiment with.
Great point to introduce some analog logic.
Yeah. The watchdog would perhaps be a separate, like a 555 timer or something. Maybe not so simple, but some dedicated chip that's good at that stuff and like starting things in sequence, and then you'd have that be like a separate thing. And the only thing there is if that thing breaks, what happens? So, yeah. Yeah.
Also on the 2 chips or microprocessor design, do you plan to use the same microprocessor with the same software, or do you plan actually using 2 different microprocessors with entirely different software? Because that's what you're doing in usual space stuff and aerospace.
Okay. Yeah, I've been considering like you have perhaps one of them has a mask ROM or something, so it's entirely burned in, and then you have a layer on top which is reconfigurable, like the Mars rovers do that, as I understand. They have the base operating system that controls like the radio and the booting process that can't be changed, but everything on top, like they had bugs in the operating system, like in the file system, where it could have crashed during landing due to running out of RAM. It didn't. Just like a few days afterwards, it started crashing. But that's another interesting. Go read about how they fixed the opportunity. I think it was. That's an interesting read.
And you maybe should come back to me about what processors you use later after the talk.
Yeah, if you have tips, I'll.
Yeah.
Yeah, let's talk.
Maybe.
Oh.
Yeah, hi. Thanks for the nice talk. I have one question.
Yeah.
What additional knowledge do you expect from a PCB designer from automotive industry?
It's just the about handling like harsh environments. Like if you look at how the power system in a car behaves, it's just having a grasp on it. Maybe you don't need to actually work with it, but just knowing that those kind of things. Maybe I'm just being like overly.
So it's
selective.
more like the schematic developer, not the PCB itself. So the circuit.
Oh, maybe I should say circuit. Yeah, I've been a little sloppy, perhaps.
Okay, thank you.
Yeah. So, but still, stuff like if there's an over voltage condition, it should handle it somehow gracefully. That'd be nice. Or if like one of the batteries produces too little. You might need a Schottky diode from each battery pack, just so they don't, like if one breaks, it doesn't short out the other and stuff like that. There's a lot of things you can do in that area as well. So, tricky. Oh.
So I don't have a question, but rather a comment. You're doing all these tests regarding the temperature conditions. And have you ever contacted one of the automotive manufacturers? Because I'm working with one, and I don't use that stuff, but I know we have like climate chambers where you can test the whole temperature range, because we need to do that for qualification.
No, yeah.
I don't know. I mean, probably these chambers don't have that much of a temperature range, but at least we have to qualify like from -40 to plus 120 degrees, I think.
Yes, that's still like rather useful. No, we're pretty
and
much.
I think it's easier to find than a launch site.
Yeah, exactly.
Which can test that.
Oh, well, we don't care about the launch stuff, and that's not our concern, luckily. It's a bit simpler. But yeah, there's stuff like that, like trying to find the people who know, because we're kind of doing it by the seat of our pants. And yeah, we haven't got, and we should start, like, there's stuff like mailing out the, like, people who work in aerospace and like just asking them, like, hey, do you have some simple tip? Because we'd rather not have to build test gear unless we have to. In this case, we're lucky that we already have some stuff for testing it. Like if we can get that cryogenic freezer thing and just stick the vacuum chamber we already have in it, then that's simple. Just put it there. But it'd be nicer to have a ready-made system for it and not have to mess around. So yeah, definitely, it's good. It's good idea. Yeah. Thank you.